Okay, we're continuing on with section 3.5. We just looked at some charts that help us to see whether a data value should be considered unusual or to be in the expected range. And now I just want to look at an example that helps illustrate how that works. So suppose that for a certain person, the average number of Visa purchases per day is 3.59 with a standard deviation of 2.81. Would it be considered unusual if the person made 12 purchases in one day? Explain. So we're going to use the z-score to help us figure out how many standard deviations away 12 purchases is from the mean, and that'll help us answer this question of, is it unusual? So for a z-score, you start off with the number in question, which would be the 12 Visa purchases. You subtract the mean, which the average it said was 3.59, so we're going to subtract that. And then you divide by the standard deviation, and they said we had a standard deviation of 2.81. So that's what we want to calculate. Bring in the calculator for that. When I go to enter that in the calculator, it is important to remember on all z-scores that because there's a subtraction in the numerator that we want done before the division, in order for the calculator to get that correct, we need parentheses around the top. So 12 minus 3.59 divided by that standard deviation of 2.81, and we get a z-score of 2.993. Remember exactly 3 decimal places on z-scores. So that would be 2.993. Alright, so now back to their question, would it be considered unusual if a person made 12 Visa purchases in one day? Because that has a z-score of over 2, that tells us that 12 purchases is more than 2 standard deviations away from the mean, and anything over 2 standard deviations away from the mean is unusual. So I'm going to say yes. 12 purchases would be unusual. Because it is more than 2 standard deviations away from the mean. So whenever you hear that question, would it be considered unusual if? Your plan of attack there should be to calculate a z-score. If the z-score is over 2 or below -2, that's going to indicate a yes to that question. Anything else would be a no. Alright, and then let's look at question B. Suppose that the number of purchases one day for this person has a z-score of -1.278. What does this tell us about the number of purchases they made? Well, the first thing it's telling us is that the number of purchases was 1.278 standard deviations below the mean. I know it was below the mean because it was negative. And then I guess I could also say that means it was in the expected range because it's less than 2 standard deviations away. And then finally, if I think about what that means, it can tell me what the actual number of purchases was. So let's write out a few things. So what does that tell us about the number of purchases they made? Let's try and find the number of purchases first. The number of purchases is 1.278 standard deviations below the mean. So to figure out how many purchases they made, I could take the mean, 3.59, and then I could subtract 1.278 standard deviations, which would be times the standard deviation of 2.81. And that should take me backwards to the number of purchases they made. So let's put that in the calculator and see if we can tell how many purchases they made that day. So 3.59 minus 1.278 times 2.81. So I get -0.0112 or 118. But there's no way that can be what they actually did because the number of purchases is a whole number. So I'm going to assume there was just some rounding error in this z-score and that it was really 0 purchases that they made. So I think that's a good place to start. That z-score of -1.278 tells us that 0 purchases were made that day by the customer. But then extra information is we now know that 0 purchases is not unusual. And I can say that because I've already seen the z-score, which is less than 2 standard deviations away from the mean, or it indicates that 0 purchases is less than 2 standard deviations away from the mean. And just notice here I wrote the number 0 and the word 0. Just pick one there. So we'll go with 0 purchases is not unusual because 0 purchases is less than 2 standard deviations away from the mean. All right, let's have a look at the final question, question C. What would be the expected range for the number of Visa purchases per day? That is, how many purchases could be made and it would not be considered unusual. So we'll fill in the blanks right here, but we need to do the scratch work down below. The expected range is anything within 2 standard deviations of the mean. So I'm going to take the mean, 3.59, and I'm going to both add and subtract 2 standard deviations, which would be 2 times 2.81. And if I do that with a minus, we'll see what we get, and let's see what we get if we do it with a plus as well. And those will be the boundaries on our expected range. So let's bring in the calculator. 3.59 minus 2 times 2.81 is negative 2.03. And if I hit second enter and change that minus sign to a plus sign, I get 9.21. So it might be a little bit tempting just to take these two numbers and just plug them into the blanks there. But and that is what you do if it was a continuous data set where negatives made sense. But this is a discrete data set and also one where negatives does not make sense. So what I want to do is think about on the number line, what is the smallest number of purchases that fits in between these two, and what is the largest number of purchases that fits in between these two. So let me draw out a number line. And first of all, the smallest amount that makes any sense would be 0, but I'll go ahead and put a -1, a -2, and a -3 on there as well, I suppose. And then going the other way, 1, 2, 3, 4, 5, 6, 7, 8, 9, and let's throw 10 on there as well. So the boundaries we just got, -2.03, that would be right about here. And 9.21, that would be just past 9, so somewhere around here. So what's the largest number of purchases that falls in between these two purple fences that I just made? It looks like that would be 9. And then 8's in there, so is 7, so is 6, 5, 4, 3, 2, 1, and 0. And so is -1 and -2, but those don't really make sense for a number of purchases. So you see that when I'm trying to think about the expected range, I'm calculating boundaries, but if it's a discrete variable, I'm also thinking about what's possible in between those boundaries. And in this case, the smallest number of purchases that fits in between those boundaries and makes sense is 0, and the largest number that would be 9 would be 9. So my answer is that the expected range would be anything from 0 to 9 purchases. And I think it's also important to notice that even if this had been a 9.71, that would have moved the purple line over a little, but 10 still would have been on the outside and 9 still would have been on the inside. So don't think of it as I rounded this to 9. I drew that 9.21 just where I thought it was. And then I thought, what's the biggest number that's inside that still makes sense? So it's not a rounding issue. Those are boundaries. We put them just where they go, and then we think what's the smallest and largest number that fits. So a quick summary of that. For continuous data, use the word between, and do not adjust the numbers at all. Whatever comes out of these calculations, leave them alone. But for discrete data like we just did, consider the smallest and largest possibilities that fall between those boundaries. And at first, while you're trying to work this out, I think drawing a picture like this is really helpful to understand why you're picking the numbers you are, and to make it clear that this is not a rounding that's happening, but just a boundary. All right, let's look at one final page here from section 3.4, which is the coefficient of variation. You're going to see as the class progresses on that it's very common for us to be estimating the mean and being focused on the mean, and we use the standard deviation to help us do that, but the standard deviation all by itself can also be important. Imagine you were trying to fill soda cans with 12 ounces, and you tested it and you found out the average was right at 12. Then should you be satisfied? Our initial thought might be, oh, sure, if we're hitting the average, we're good. But I would say that's not true all by itself. What if the standard deviation that went with that mean of 12 was 2 ounces? Then that would mean it wouldn't be unusual for us to miss our target by 3 ounces. So what if you bought a 12-ounce can of soda and it only had 9 ounces in it? You wouldn't care that there was other ones balancing that out. You'd be mad about your can. So people in a process like that, they like the standard deviation to be small because that shows that they have a consistent product. But what does small mean? Is missing by 3 ounces bad? It can be. I would say missing by 3 ounces on a 12-ounce can of soda is horrible. But if you missed by 3 ounces when you were filling a 100,000-gallon pool, then I would say that was fantastic. So when you consider, do you have too much variation or is the variation at an acceptable level, you want to think about the standard deviation and how that compares to the size of your target, which was the mean. So the coefficient of variation helps us to do that. We look at the ratio of the standard deviation to the mean of the data set when we're doing the coefficient of variation. And what that looks like in symbols varies depending on whether your data came from population or census data or sample data. If you had population data, then your coefficient of variation, or CV, is sigma over mu times 100%, but in words that's the standard deviation divided by the mean times 100%. For samples, in words it's the same thing, standard deviation divided by the mean times 100%. It's just if it's samples, that would be a sample standard deviation S and a sample mean X bar as opposed to population ones mu and sigma. So let's see how that plays out with an example. A supermarket has 10 registers open. Each register has its own line, and customers ready to check out pick the line for the register they wish to wait for. An electronics store has 10 registers open as well. However, they have one single line that all the customers wait in. And when a register opens up, the first customer in the single line goes to the register. The wait times at the supermarket have a mean of 5.7 minutes with a standard deviation of 3.207 minutes, and the wait times at the electronics store have a mean of 8.75 minutes with a standard deviation of 1.574 minutes. So let's calculate the coefficient of variation for each of those. We'll start out in part A looking at that for the supermarket wait times. So we want to come up with the CV, and we want to take the standard deviation divided by the mean times 100%. So let's see, for the supermarket, the wait times for the supermarket have a mean of 5.7 and a standard deviation of 3.207. So according to the formulas, we take the standard deviation, 3.207, we divide that by the mean of 5.7, and then we multiply that times 100%. That times 100% as part of the formula is optional. You could just do that division and you'd get the decimal form, and you could just convert it to a percentage by moving the decimal over, but it is usually written as part of the formula, so I'll show it to you that way. So 3.207 divided by 5.7, that would be our decimal version, and then times 100 to get that to be a percentage. And we would say it looks like the coefficient of variation is 56.26%. So approximately 56.26%. On all percentage type interpretations, it's common for us to say at least 4 decimals. Well, this has moved the decimal over, so I still have 1, 2, 3, 4 if I was thinking about the decimal version. And then let's just practice that again. Let's look at what it would be if we were doing that for the electronics store. So I'm going to just do that in pink just so we can kind of separate the numbers here. But for the electronics store, our mean was 8.75 and the standard deviation was 1.574. And so we're going to do the CV in the same way. Now that I got that kind of pink label, I'll go back to the blue. But what's our standard deviation for the pink one or for the electronics store? 1.574. And divide that by the mean, which is 8.75. Again, that in my mind gives us the percentage just in decimal form, and I would slide the decimal over kind of on my own, but this formula builds that in by doing the times 100%, so we'll go ahead and follow that. So 1.574 divided by 8.75 and then times 100%, and as a percentage that would be 17.99%, an 8 but followed by that other 8. So 17.99%. So it seems like actually calculating the coefficient of variation is not that tough. It's just a division and then a multiplication with that 100%. So it's pretty quick to do that. Let's look at the follow-up questions and see what that does for us. Would it be unusual for a customer to be in line for over 12 minutes at the supermarket? So let's see, that's actually going back to our previous section. They're asking us, would it be unusual? So I want to do a z-score for that. So over 12 minutes, I'll look at the borderline number of 12, and this is the supermarket, so we're going to use these numbers, subtracting the mean of 5.7 and dividing by the standard deviation of 3.207, and doing our z-score. So parentheses 12 minus 5.7 over 3.207, and we get 1.964 as our z-score. So would it be unusual for a customer to be in line over 12 minutes at the supermarket? Almost. Not quite, because it's under 2 standard deviations, but it's very close. So I would say no, because 12 minutes is less than 2 standard deviations above the mean. This isn't a huge deal, but I did actually say that it's talk about above the mean instead of away from the mean. They're only talking about long wait times here, so I want to point out, no, that's not an unusually long wait time, because it's not that many standard deviations above the mean. You could still say away, but I kind of like to emphasize the direction since they're talking about a specific direction. So even though the average wait time at the supermarket is 5.7 minutes, this is telling us we shouldn't be surprised if we end up in that line for 12 minutes. So we know that the average at the electronics store is higher, and we're going to look at the same question. Would it be unusual for a customer to be in line for over 12 minutes at the electronics store? And we would do that same approach. We do 12 minus, but then the mean for the electronics store is 8.75 minutes, and the standard deviation is 1.574 minutes. We go through to our z-score, same calculation, just different numbers plugged in. So 12 minus 8.75 over 1.574, and look at that, we end up over 2, so 2.065. So there's not a huge difference between these in terms of the size of the numbers, 1.964 versus 2.065, but we had to draw a line somewhere and we drew it at 2, and this one is less than 2, this one is more than 2. So when they ask this question, would I be surprised, would it be unusual for me to be in line over 12 minutes at the electronics store? I'm going to say yes, because 12 minutes there is more than 2 standard deviations above the mean. So I think that we have an interesting thing there. The wait time at the supermarket on average is less. It's about 5.75 minutes and 8.75 at the electronics store. And so we kind of expect to wait in line longer at the electronics store. But let's say that we were in a hurry and we needed to be out in 12 minutes. It would be a surprise if we didn't get out of the electronics store in 12 minutes, but it wouldn't be a surprise at the supermarket. And that turns out to be the case. You get a more consistent wait time with less standard deviation typically when you use one line that feeds many registers, which is the Best Buy model or the Fry's model, as opposed to the Safeway model where every checker has its own line. And that turns out to be true even if they have the same average. So as a customer, you really should prefer that you have one line feeding multiple registers instead of having to pick your line. And personally, I feel like I always pick badly and end up in the slow line. So I prefer those long lines. I don't have to make that choice. All right, let's go ahead and look at one final question here. And I think we probably kind of discussed it right up there. But if having individual lines at each register and having one single line for all registers is known to produce the same average wait time, which it is supposed to do theoretically, then is there any advantage to having a single line? And I would say yes, because the standard deviation is smaller. You have this smaller coefficient of variation, meaning you get a more consistent wait time. And people like consistency. So if the average is going to be the same, it would be good to have a consistent wait time so you don't have some customers getting through quickly but others getting frustrated in a slow line. So I would say yes, there is. a smaller standard deviation deviation means the wait time is more consistent for all customers. And I would like that as a customer. There's kind of less of a luck factor in terms of how long I'm in line. And there's less frustration. I don't know, it could just be me, but I always get frustrated when I feel like, oh, I picked the wrong line, and I look at that other line I was considering, and I see that the person that took the spot I would have had got out, way before I did. And that sort of thing just isn't going to happen if you have that single line. It's kind of a more fair situation. And so they're going to that at more and more retail places to have that one line idea. I think even our bookstore here at Chabot does that during the busy times. And again, it's already frustrating what we're paying at the bookstore for our materials, so let's have one less thing to worry about did we pick the right line or the bad line. All right, that wraps up section 3.4.